you said like only
Akshay, so it's my recording is working, so you can start. It will
yeah,
record the screen and the audio as well.
that's great.
Yeah, sounds good.
Okay.
Start please.
Okay. Let me try to connect again. Just give me some moment of time. Like I tried connecting from laptop, so it's basically installing that spinach here, but it still didn't come. So I'll go and continue.
Yeah, sure. No worries.
Oh yeah. So yeah. Is my screen visible?
Yeah. Yes, it is visible.
Okay. So the screen is visible now. Entire window.
You
Like a
have opened your Meet tab, right?
yeah. So okay, fine. So there
Yes.
are like two options, right? Entire screen and window tab. So yeah. Just give me a sec. Yeah. So like yeah, it was quite hard to write via with the help of mobile. So yeah. No, like mobile, no, sorry, mouse. So yeah, moving ahead. So your task specifically, Suchi, is quantum transformers.
Okay.
Yeah. Hope my handwriting is
No,
quantum
it's
transformer.
good.
Yeah. Yeah. So this is your task. Quantum transformers per se means like finding quantum circuits using LLMs, not using LLMs per se, using transformers. You can use LSTM, but like this is a long sequence task. So specifically, transformers is like recommended. You can explore other architectures as well. Titan, Mate. There are like Mamba is one of the architectures now, but transformers is like you can say crown jewel of this. So yeah. So finding quantum circuit. So I will walk you through what exactly is like what exactly we are expecting and the details of this finding quantum circuits via a neural network architecture. That's it. That's your tasks, like tasks. So this consists of having a long sequences. So that's why LLMs like transformers, LSTM, GRUs, Mamba, and that kind of like neural network architectures are recommended. So yeah, moving ahead. So okay, just give me a sec. There should be a page addition here somewhere, or I can directly move this page. Okay, here is add option, new page. Okay, fine. So yeah, so from the start, what exactly we are planning to do? So let's say you must be aware of this concept. So this is basically a quantum circuit. So this is your input state, right? And this is your output state. Okay, and this is your unitary. So this is a single qubit unitary circuit, right? So this unitary circuit is nothing but, if you write it in terms of Heisenberg quantum formalism, this will be a 2 cross 2 matrix. Will be having a unitary constraint, and if you try to parameterize this per se, you can parameterize this as a function of theta, phi, and psi. So these are nothing but your quantum angles. Function of this is f. This is function of theta, phi, and psi. So what exactly are these quantum angles? Are nothing but you will be having four elements, right? This A element, B element, C element, D element. These will be the functions of theta, phi, psi. So what exactly is a 2 cross 2 parameterization? You can try to find this online. This will be a circuit which A element will be a function of this in terms of some cosine sine, like that. Exact 2 cross 2 like unitary you can find. So that is what we're trying to do per se. So I hope this point is clear. This is the point. So what we can do specifically is, second is, let's consider application of classification. So let's say you have your input vectors uh, and your output vectors. So in your input vectors, what specifically are your input vectors for classification? Are nothing but your image pixels, which are you're converting into digital format, and then you're quantum encoding it, right? Those will be your input vectors, and what will be output vectors will be nothing but the target vectors, which we discussed on the our first meet, right? So this is limited to classification application. So you can think of generation applications as in generative AI. In it, what will be the input vectors per se? It can be a text. So let's consider text to image application. So input vector in that case will be your text or your sentence converted into some form of vectors, like concatenation and some form of vector using some embedding. And what will be your output will be your image vector, right? So for various tasks, you can find the input output pairs. So hope this point is clear. Now we'll move on to the third point. So what exactly like in specifically in quantum computing, if you look into your input vectors at the start, qubit is in ground state. Qubit, all the qubits are in ground state. That is what we're assuming. So that's why the input state will be your this, right? This will be your input state, right? Now you will have to find that unitary such that this unitary will map this state as in only the first element will be 1 in 1 0 basis, and remaining all will be 0, whatever will be the number of qubits. You will have to find that unitary. Now this we are having a different representation here. It is not represented in terms of qubit, but what we're doing is basically applying a unitary matrix to the input vector such that it will map to our input vectors, as in what this input vectors will be your quantum encoded vectors. So your quantum encoded vectors will be what exactly? You have studied that 5 encodings, right? A novel density matrix encoding cannot be done here, so we can ignore that, but the 5 other encodings can be implemented here. Specifically the 4 encoding vector encodings, what we have like this dealt with: binary encoding, angle encoding, phase encoding, and amplitude encoding, all can be using this framework can be done. But unitary encoding will have to undergo, this will be your per se that circuit. Instead of having this as your quantum state, or this as the quantum state, this will be your circuit representing that unitary of that image, and this will be your vectors that will be using to infer what exactly is the classification output, as in which classification does this given unitary belong to. That is different from the 4 vectors encoding and using this. Okay, so this will be your unitary of input mapping. Okay, unitary of input mapping. So how to find unitary of input mapping? You already know. If it is within the classical computational power, you can if you are having an access to a supercomputer, a rough limit will be a 40 qubits. So that is the maximum extent that you can go up to, 40 qubits, as in you can access a 2 raised to 40 cross 2 raised to 40 matrix. It may be plus minus, it may be -2 -3 qubits, but this matrix you can per se find. This is the classical computer limit per se. So hope this is clear. This is your qubit vector, and this is your input vector, right? This is the first step. Now third step. Now what will be, like the next step will be as similarly, like once you have the input vectors, you can find a unitary matrix to convert it into output vectors, right? So this input vectors to output vectors, as in what will be your output vectors in this case? Target states. Okay, this will be your target states. Fine. For training per se. Okay, this we are studying per se for training. So like this will be our target states. Now this will be input to output mapping unitary. So how to find this unitary? You know, right? This will be found by SVD, or this will be found by ML, or this will be found by QR. And since we are in the classical computing limit itself, you can use these 3 approaches, right? So once you have that unitary matrix, like hope these 4 points are clear. Now moving on to the next point. So what you can do next is, since the quantum computer doesn't understand the language of vector, doesn't understand the language of matrix, what it understands is a unitary evolution. So, and following the Heisenberg quantum theory and the conventional quantum computers present here, we can convert a unitary matrix, any unitary matrix, to certain approximation into U3, into tensor products, tensor products, and multiplication, and multiplication. Yeah, multiplication. Yeah, so forgive my handwriting. Like I'm specifically not using a pen here. So I'm using directly my like finger, so that's why so actually pen is not working. I have to download another app for it, but I'll be ready in the next session. So anyways, so unitary matrix, it will be 2 raised to n into 2 raised to n. So essentially what this 2 raised to n implies, these are nothing but the number of qubits here. Okay, number of qubits. Okay. Okay, fine. So what we are basically discussing, you can convert this unitary matrix having dimension of 2 raised to n into 2 raised to n into tensor products and multiplications of U3 having 3 parameterizations, phi, theta, and psi, right? And CnOT gate. A CnOT gate will have 2 parameterizations. What is your control qubit? What is your target qubit? This will be a 2 parameterization. As in, you can write any quantum circuit of any length into this conversion. So how we can tensor decompose this given unitary using a algorithm called as quantum Shannon decomposition. So you can have a look how exactly is a transpilation done using Qiskit transpiler, but we have like provided you the code for it. So you're keeping it as a black box for now. This is your like you're basically converting this. So if you want to write per se, to understand this further, let's consider a simple a bell state, right? Bell state, as in this is a bell circuit. So what state will be getting at output is 1 upon root 2 0 0 plus 1 1, right? This will be your state at the output, and this will be your input state, right? So specifically how you can write this in tensor notation format, like h tensor psi multiplied by c naught, right? And this h you can write in terms of u3. U3 will have certain parameterization, theta, phi, and psi, because you can write it in terms of 1 by root 2 minus 1 minus 1 sorry 1 1 1 minus 1. This format you can write it into a 2 cross 2 matrix. You can parameterize this unitary. This will be 3 quantum angles that will be parameterizing this unit. Okay, so you can write it in this format. So control gate will have what? This will your first qubit, this is your second qubit. So this will be your control state, either first, and this will be target second. So this will be a conventional notation. You can experiment with this. There are other notations of writing this decomposition as well. So you need not follow this convention. Whatever is given in the code, that is just one of the way, and you have to code that as well. So what we have given the code for is converting a unitary into this setting, as in you will be getting a transpiled circuit, but you will be not getting this algebraic notation format. So if you can read there, like in the code itself, we have mentioned in the comment that you can follow any kind of convention for converting from this into this, as in there are other ways as well. So this is just one of the ways of writing. Okay, fine. So if you'll write this in terms of this h tensor I into c naught, this 1 comma 2. If you'll follow this convention, what exactly this is nothing but a sequence, as in what you're writing in terms of words. So what we were expecting, like what we are expecting from you guys, is to convert this is nothing but a simple text, convert this into word embedding, as in that also is a point of research, like whether to take a U3 single unitary, then or tensor protected like state total state as a single embedding, or you can take it as a separate embedding. As in H, you can take U3, theta, phi, psi, a single phi 1, 2, theta. I will explain you to this full example, so you'll have a clear cut understanding. You can convert this using some already existing model of text embedding. OpenAI is one of the model that is available. You can use Gloway. You can use other kind of embeddings. So what basically this will do is convert this U3 theta theta 1, theta 2, theta 3 into a vector setting, which will be n cross 1 or n cross 1. So let's say use a different notation because n is used for qubits. M cross 1. This will be a so m will be decided by what model you're using, basically for converting this into vectors. Okay, then you can convert this tensor product into notation of this m cross 1, right? You can convert this into a vector kind of setting. So what this will form is basically your input for the transformers you are going to train. We'll go into details of what exactly transformer is and now what is that circuit, but hope this is clear for now. Okay, so this you'll have to do 2 times, right? As in for input, so you'll have to design specifically 2 transformers. So if up till this point is clear, so I'd like to go through the previous few steps. First is what? Unitary of mapping from input qubit or ground state of the qubit to ground state to your input state, right? And this will be like how many input vectors you will be having, that many unitary circuits you will be having. Okay, and similarly unitary mapping from your input to or output, input to your target. Okay, input to target. This is clear. Now you will be converting this both into your transfer setting and writing the algebraic notation for it, converting it into transfer setting, writing algebraic notation for it. Okay, fine, this is fine. Now we'll go through what exactly transformer architecture is, but we'll first like to discuss what are the inputs and the outputs of the transformer architecture, what we are planning to train. There are specifically two transformers architecture one. So first architecture we'll discuss here, what are the inputs and outputs of that. Okay, yeah. So if this is your transformer architecture, we are keeping it as a black box for now, but we'll go into details what exactly they are. Okay, so like you will be providing input vectors as in the sequences of your circuit here for first. So this will be a U3 as in unitary, first unitary, what we discussed previously, first unitary, and this will be your sequences of the vectors, that will be your input data, right? And let's say you're taking this for n is equal to 1 qubit. Okay, 1 is equal to 1 qubit is very less, as in you will be getting just 2 cross 2, and it is not possible to convert it into target state. So we'll start with n is equal to how many number of classes you will be having, that many number of specifically for classification tasks. So that many number of qubits you have to take. So for MNIST data set, there are 10. So you'll be specifically taking 4 qubits, or you can take 3 qubits as well. In 3 qubits, like you'll have to assign the target states accordingly, and that changes, like you can do with the research of target states. Like instead of taking at equal spacings one, you can take ones at like multiple spacing and try to create a new state that is maximally separated, and it will still give the result. So we can start with n is equal to 3, then n is equal to 4, n is equal to 5. Let's go up to n is equal to 6, depending on what your computing power is. So like we'll start with n is equal to 3. You got your unitary, as in what this unitaries will be, number of, so what are this number of unitaries? It will be 50,000 or 60,000. For MNIST data set, it will be 60,000 unitaries that maps from qubit input state to your output state. So code for that is provided. So this 60,000 unitaries are already found in the code for MNIST data set. Now okay, fine. Yeah, so this vectors, so you have converted that into algebraic notation, then you have converted that into using embedding model into sequences of vectors, and then you'll be providing it to transform models, and the output of the transformers is where you'll have to pay attention. So what exactly is the output of the transformers? So you're expecting the next sequence from here, right? As in, if you're given a sequence, so you're taken a unitary for n is equal to 3, and this is your input unitary, let's say, and you want the output for n is equal to 4, right? N is equal to 4. That is the output that you are expecting. So you have to use encoder and decoder architecture. This is same as mapping from a English language to a French language. So this problem can be mapped to this setting, where your English language will be corresponding to n is equal to 3 qubits. Your French language will be corresponding to n is equal to 4 qubits. Okay, and that means what you'll be finding here, as specifically this will be our input, and corresponding for this given network, what should be the corresponding this vector. What for this given, what will be the corresponding this, as in the sequence of that will be for n is equal to 4, and you have this training data for n is equal to 4. Okay, you have this training data as in the sequences that you have to convert into text vector format, and then so basically for transformers, the output will be in the form of this output will be form of u3, theta, phi, psi, and CnOT, right? And you will have to research this as in how many number of U3, how many number of output tokens in the transformers you want, how many numbers of output tokens in the transformers you want. As in, if let's say your spacing, so you know the quantum angles not 362 plus 360 and like minus 362 plus 660, but in radian format varies from 6.26, that is 360 minus 362 plus 360, like 6.26. So you will have to decide your spacing, what spacing we will have to work on. You can decide the spacing to be 0.3 or 0.5 for convenience. So how many number of examples you will be getting from here is nothing but this into 2 divided by 0.5. This will be the number of tokens, output tokens of U3 that you will be training, right? This. And you will be having CnOT tokens. So CnOT tokens, how many number of qubits you are having or you are planning to train, that many number of qubits should be here. As in CnOT permutations combination you have to do. What is the control qubit and what is the target qubit? So let's say you are starting with 1. Here it is 2. Then you can have it a 2 comma 1 as well. So how many number of qubits you have or you plan to expand to, that many number of permutations you have to take of CnOT. Of this control gate and target gate. Hope this is clear. As in, if it is 3 comma 2 or it is 3 comma 1, all the permutations you have to take in the tokens. So CnOT, it's not there to control in your hand. You have to take all the permutations, but U3 will be there in your hands. As in U3, what is the period or what is the difference between the two quantum angles you want, so to classify the R network. So this 0.5 is for convenience, because this size, if you look into, will expand very if you take the spacing as 0.1, this value of 0.01 comes out to be 1252. And if you take the number of permutations for that 1252, p of 3, because you have to choose 3 angles from it, right? So if you calculate this will be a very big number, as in 195781500. I just now calculated it. It will be very large number. And if you look into chat gpt and all, the tokens they have trained on are just 50,000. So you'll have to adjust that, because we don't have that kind of compute power. So the spacing can be taken for convenience one as well, because that will limit the computational number of tokens what you have to train on. So what this circuit basically will be doing is you'll feed in the first training circuit. What specifically will be doing, you'll be feeding in n is equal to 3 setting algebraic notation format, and it will be similar to language translations. Encoder decoder architecture will be there. What this architecture exactly is, we'll go into details in the next two three slides, or next after the 2 3 slides. What output you'll be expecting for n is equal to 4, then you'll be giving this as the output, and you'll be expecting the output for n is equal to 5. This similar architecture you can expand up to n is equal to 40. That is the thought process. Or n is equal to 40, because you have this as the training data, right? This is the computation limit. But for you guys, you can try it just for n is equal to 5. That's it, because you don't have that kind of computational power, and this period also you can adjust. So without going to n is equal to 40, we can try for n is equal to, let's say, 5. That's all limit. Like, you will provide first transform architecture n is equal to 3 data. What will be getting as output for n is equal to 4? You have this training data, then you will train the transformer. Then you will pass on n is equal to 4. You will train the same transformer for n is equal to 5. You will pass n is equal to 5. You will train that. You will stop at this. Okay. This is your first transformer. Now moving on to second transformer. Like, what second transformer architecture training is. So okay. So what we have trained till now, just the input unitaries. Now we have to train from input to output mapping. So what exactly second transformer will be doing? It will be similar to language transformation, but here the number of words in the input and the output will be similar. If you try in the previous case, the number of output words will be greater than the number of input words, because the circuit will be larger, right? The algebraic notation for it will be larger, for n is equal to 5, n is equal to 6. But for this case, specifically, it will be a specific case of language translation only. So language translation, as in what we'll be doing here is, specifically, you have your input unitaries, right? For n is equal to 3, 4, 5. You have your output unitaries. For input and output, what I mean is, first unitary, what we discussed, and the second unitary, what we discussed previously. So you have 60,000 your for all the we have the 60,000 for all the MNIST data set, and we have the 60,000 for all the MNIST data set. Okay. And you have also this for n is equal to 3, 4, and 5. So what you will be training the transformers for is, this is your input, you want this as the output. This is your input, you want this as the output. This is your input, you want this as the output. This you will be training the transformer architecture for. It will be similar to encoder decoder architecture we will be discussing in the next slide. So hope this point is clear. We'll now go into details of what exactly is a transformer architecture we'll be using in this case. So if you have any questions, you can ask. So hi Suchi.
Hello. Hi.
Yeah. Any questions from your end?
No, that's cool. It is
Okay,
only
okay,
a simple process. Yes, that's
okay,
it.
okay, fine, fine.
Yes.
So moving on, what is a transformers architecture? Fine. Okay. So, I'll explain it in very simple terms, so it will be easy for you to understand. So, let's say you have your okay. I'll start with this. So, you'll have your input vector. Let's say for convenience, we're taking just a simple input vector. Input vector will be what? Your text embedded input vector. So, let's say I am here. Okay, I am here. So what you'll be doing is you have taken your I and you are embedded into vectors. So single vector we are considering. We're not considering m and here as well. A single vector once we are considering here, you'll be like assigning it to a position. So what exactly is a vector position in this sentence, right? Position encoding. So you'll be appending your or adding your position encodings. It will be in sine and cosine format, or there are different kind of position encodings available. Like this is one of the encodings that was used specifically in a transformers paper. So we will use that here. I think just for demonstration purpose, we'll add this both encodings. Whatever output will be an input to a encoder architecture. So what exactly is encoder architecture, we'll be going into details of, but for now just consider just the black box, and this is your input given to the encoder architecture. The output of this encoder architecture will be given to your second encoder architecture. So what exactly are these encoder blocks? It will be nothing but in some like in sequences of self attention plus feed forward, self attention feed forward, like that. So this will be a one architecture, and before that there are query key and volume matrices. So we'll go into details of encoder architecture. This will be encoder architecture 2, like that, so on. So the output from your nth encoder, let's say this is nth encoder, the output from your nth encoder will be given to the second layer of the decoder. Decoder first block will be here, as in the self attention decoder first and the feed forward first, and this will be given to your value matrix. I'll have to check it once again. It will be given to your value matrix of this input, and this decoder will be your query. Okay. Yeah, query and key. You will be giving your input from your output from your decoder to query and key, and this encoder output will be given to your value matrices. We'll be discussing that in detail. This will be a decoder block 2, and then up to so on decoder block n, and from your decoder block you'll be having uh, your output classifiers or output tokens here. Okay, output tokens. Fine. So we'll discuss in detail. Hope this is clear. So the figure is not that much clear, and I can understand. I'll try to rectify it from the future lecture. Like I'll try to install the proper app for which can utilize the pen. Okay. Anyways, moving on. So what exactly is the encoder architecture? So we have discussed the input. So let's say the text embedded vector and the positional encoded vector are concatenated or added, and you got a single vector. That single vector will be for training purposes your query vector, your key vector, and your value vector as well. Whenever the architecture has a decoder, that same vector will be a query vector, that same vector will be key vector, for that same vector will value vector for training. Okay, so this is clear. Now this you'll be multiplying this with the weight matrix, that is called as a query matrix, which will be having the dimensions of this. So whatever dimensions are here, it will be a square matrix of that dimension. Let's say this is M, so this will be M cross N matrix. Similarly, key will be a M cross N matrix, and value will be a M cross N matrix. Okay. Now, this is the first stage. Okay. So this what we're discussing specifically is the self attention of the encoder block. Self attention. So after this, you have to take a dot product between this. So if you look into the notes provided, so dot product I think so is explained there. So what exactly is a dot product is if they are in the same direction, they will have one as the value. If they're in the opposite direction, they will have a negative one as direction, like a negative one as the value, and you can find a cosine of angle between them. So that value what you get is nothing but a dot product. Yeah. So the you can have a look at, so cosine theta formula you can write, right? A dot b upon mod of a into mod of b. So that mod of a into mod of b cosine of theta you can put here, and this is nothing but a bar dot b bar. Okay, this is in vector format. Fine. And what we are multiplying, and what we are getting is nothing but a vector. So this will be a query key transpose. This will be your attention score. Okay. Okay, so this whatever value you'll be getting, this will not be an attention score. This will be a weight matrices, not weight. So this will be a weight vector. What you'll be getting. So this will be whatever query and key transpose you will be dot producting. You'll be getting a single value as output, and then like those will be attention scores, and this weight will be then multiplied with this weights will be then multiplied with your value vectors. What will be getting as in w1 into v1 plus w2 into v2. So these scalars will be multiplied with your value vectors, and so on, to get your final vector, right? So this is your transform vector. So this transform vector will be your output of your self attention. That's it. So once you'll be having your output of self attention, then we'll be proceeding with the feed forward neural network. So yeah. So you have your vector, you have your feed forward neural network here. So how many m cross n? You'll have m cross 1 neurons here, and you'll have a hidden layer here, and you'll have a output layer here. Okay. Yeah. So this will be a fully connected layer. So you can expect this lines, and this will be having weights as the parameters, and you can have a look at that. So it will be having an activation function of tan h. You can use other activation function as well that are good for NLPs, and you can have a research through of transform architecture from your end as well. So it will be having an output vector that will be a same length of this, and we are forgetting that after every step there is a normalization point, as in after multiplying with query matrices, like at the end you will have to norm that vector. Basically you have to limit that length of that vector should be 1, as in the Euclidean norm of that vector should be 1. Okay, fine. After this also output you have to norm that will be 1. Okay, and there are some like residual connections, as in to avoid specifically vanishing gradient problem. What you can do is, whatever output is there, you can concatenate the output here. So this output what you're getting from here, you can concatenate the output here. Okay, so that is nothing but a residual connection. You can have a look at that as well. So hope this is clear. This forms your first encoder block, and so this is for training purpose. Okay. Fine. Fine. Are you aware about the decoder architecture? So the output of this we have already discussed is
Little bit.
yeah. So if you're aware about it, like we can skip that session and we can move forward with the code. Or if you are like new to this, I can suggest you the reading material. Like this will be, if you are anyways new, this will be abstract information for you. But hope the quantum part is particularly clear. This we cannot cover in limited set of time here, so I'm just giving an abstract level overview. But the quantum part is clear to you, right?
Yes, that's correct.
Yeah, that's clear. That's all that's required. So to conclude this, whatever vector you'll be getting from your encoder block, you'll be giving it to the value matrix, as in multiplying the value matrix with the second decoder block here. The first decoder block will be having your self attention and your feed for a neural network, and the output of this will be given to a query and key matrices. So what exactly this will be? This will be your n is equal to 4. So you have to adjust the length. You'll have to adjust the length, as in you'll have to pad the values. So here padding is not necessary. The padding for n is equal to 3 will be necessary to make the sequences length same. So that needs to be done. So that also consideration. So there are like many things to research here. So I can agree that 1.5 months is not a time, but you can try researching through. So yeah, yeah. Anyway.
Yep, sure then. Akshay, is there any documentation for this problem statement or just walk through? is only.
No, no. So this is our novel research and novel problem statement that we're coming. So you will not be having a particular documentation of this. You can find a documentation of translation differently. You can find a documentation of transformers differently, and then like you'll have to work through the problem statement.
Yep, sure. No worries. I'll do that.
Yeah. Okay. So moving on, the output here, what will be the tokens, what you have discussed, right? So let's discuss the output part, and then we'll conclude the transformer. This is only for training. For inference, that's a whole another issue. I also recommend transformers, reading the transformer architecture. You'll have to infer from the decoder architecture itself. So let's say you're passing again your n is equal to 3 statement. The output should be n is equal to 4, right? So that output inferencing needs to be done via the output. So as in whatever output vector you'll be getting, you have to again provide that to the input of your decoder block, the first part, and then like for start you have to initialize the token with a pad vector, and then that will act as the initialization to a decoder block for inference. And whatever like once you got the first let's say translation, as in the first word translation, that will be a first word. That first word you have to again put in the decoder block's input, and then the process will continue. So inference is different from the training part. So have a look at that as well. Yeah. Okay, anyways, moving on. So we were discussing the uh, output tokens. So what are the output tokens here? We have already discussed the output tokens, right? So your U3 phi, let's say k. Yeah, k is a okay notation. We have not used that anywhere. Theta k, and let's say this will be your psi k. Okay, so this k is nothing but decided by your permutations and combinations, because so entire English dictionary will be tokenized by some words. So ChatGPT uses 50,000 words. You can tokenize it with the characters form, as in A, B, C, D, and the numbers that can essentially represent any word. But it has certain limitations that whenever there is a misspelling, let's say you are trained your LLM model, there is a misspelling, then characters will have a certain like training issue. So that also need to be explored. But let's say like we are having we are not discussing that LLM here. We are particularly limiting that to our problem statement here. So what will be our output tokens here? U3 theta. So this theta k are nothing but what is your period value, as in so it will be dependent on minus 6.26 plus 6.26 into so this will be nothing but 2 into 6.26, and whatever period you are deciding, as in the k is equal to so 2 into 6.26 upon the period. So whatever period you will be deciding. So for limited set of computation, you can decide this factor to be a larger value, let's say 0.5. So that circuit approximation, then if the transformer circuit is scaled accurately, then this will be a error rate in the angles. So U3 what will be having will be errored by this, and you can exploit the factor. So this is at the initial state of research, but you can exploit the factor of periodicity and trigonometric angles. So what your unitary will be a function of sine thetas, cos thetas, as we have discussed in our first lecture itself. So that function will have some periodicity. This sine theta will have some periodicity, right? So that can be exploited, and you can limit this range instead of going from minus 6.26 to plus 6.26 for particular problems. Like you can limit the statement as well. So for start, we'll have a whole state range, and then we'll divide it with this as in what period you are expecting. You can try increasing the value for start. Okay. So what exactly your tokens will be? Basically this U3 and this angle. So all permutations of these angles. So if you are taken this as a large value, this value will be limited lesser than 50,000. If you are taken this value, so try lesser than 50,000, you can try with 1024 and that range number of tokens. So adjust the period in this format to get this. So hope this is clear. U3, this is fine. Just for U3, I'm saying. So for CnOT, how many number of qubits you have? All the permutations, combinations of CnOT you'll be expecting here. So as in CnOT, target, control, control, targets, right? So for 4 qubits, it will be what? 1 comma 2, 2 comma 1, all the combinations of that. 3 comma 1, 1 comma 3, 1 comma 4, 4 comma 1, like that. And 1 comma, like I missed something, you can add 2 comma 4 and 4 comma 2. So these all combinations will be there in your CnOT for n is equal to 3 to 4 translation. But how many qubits you're planning to like train on your transformers, that many qubits should be there, all permutations of CnOT, right? So you can't have this as in your hands. So let's say you're trained on 70 qubits, so all permutations and combinations possible in 70 qubit, that should be included in token range. So yeah, are there efficient ways to do this for higher scaling? There might be, but this is our initial stage of the research, so we'll be limiting this for training to 5 qubits, and later we can try for more number of qubits. Okay, so fine. And yeah, the sequences are also the matter here. The sequence is another point of research, because in transformers the sequence, as in the token size, is limited. Like it's better than LSTM, it's better than GRU, it's better than RRM, but the token size is still limited to certain value, as in how many vectors you can embed in the start, the token size, and depending on that, your computational limit will be decided. So this token size is limited. I don't know the exact number, but it's limited. So yeah, so for larger circuit as well, a better translation is required, a better translation algorithm is required for your optimized training set, data set. Or you'll have to find a better representation of your algebraic notation, whatever you'll be using, right? What we discussed in the start, that better notation will be required. So those are like points of research, but what we'll be expecting from you is a preliminary research and preliminary implementation of this for n is equal to 3 to n is equal to 5. That's it. Train the model transformer architecture for n is equal to 3 to n is equal to 5. That's it. That's all we'll be expecting from you. The result may be improved later, but for now we just ask this implementation, and yeah, and you can try optimizing the result as well. So hope the problem statement is clear in detail.
Yes, Akshay.
Yeah.
That's it.
So moving on, like I'll be cutting the session from here. I'll be joining from laptop to go through the code. The code section will be concluded in just 5 minutes, because there is nothing in the code document.
Yes, cool.
Yeah, just give me.
No worries. I can explore the whole code as is it is written in Python, no? So that's not big deal.
No, no,
We
like
can.
I'm joining from laptop. You can have like we have in detail discussion about code as well. But like the code is self-explanatory, so that's why.
Okay.
So, Suchi, like whatever encodings we have discussed from the start, you see, if you want the documentation for that, we have mentioned in the code, there is one paper on the novel density matrix encoding. It is all the encoding. But apart from that paper, like there is no other documentation related to it. Like there is one proprietary document but I can't share it to them. So, like, yeah, I'm the sole author for it, but I was part of an organization, and that's a total different project from this. But the basics of encoding are explained there as well.
Okay.
So, hi. Is my voice
Hello.
audible?
So
Hi.
we shall stop this.
Yeah, yeah. I joined from laptop to explain the to you. Like,
Okay, okay.
By the way, you both are so hardworking. It's been 1 hour session and explaining and all.
so is my screen visible?
Yes, I can see.
Okay. Fine. Just okay. Yeah. There is some issue. Just give me a sec. Why does it always open in .py? This format, it should open in, yeah, news. Okay. JSON is also showing. Okay. Should be 19 already. Yeah, I'm just still in this format. I don't know. Just give me a sec. Yeah. Increasing number of qubits. This is updated, right? Yeah. But there is some directory issue. I don't know. Yeah. So this is your task. You can go through what is written here. So particularly designed for amplitude encoding. So you have been already made aware of this code. What exactly this code is does is basically you can uh, so basically this is converting it into arrays as in a vector notation. First you are converting that digital image into numpy array using IDX to numpy conversion, and then like you're converting it to arrays. Sorry, vectors. Vectors. This is the thing with the numpy of that vector for all the separate classes. Fine, and then like this is fine. And per se, just for demonstration purpose, here n is equal to 4 is utilized, but you'll have to utilize all that this n values around 2 to 4. Okay. So yeah, so this specifically can be extended to a larger number of qubits. So basically this what this code basically does is so yeah, okay, okay, just give me a sec. Yeah. So like above implementation is just for demonstration purpose. In and this specifically definition, what we're doing is specifically processing the data set for n is equal to 2 qubits, n is equal to 4 qubits, n is equal to 8 qubits. So why this specifically number of qubits are taken? Because of your vector, as in this is amplitude encoding, right? So so for n is equal to 2, you'll be getting a 4 cross 1 vector. So you'll be having an image of 2 cross 2 pixel, right? For 4 qubits, you'll be having a 16 cross 16. Uh, just a sec. Yeah. These n values are different from your n. So at the time of coding, I remember this is way back. Just give me a sec. So this n specifically represent your image size, and this n values and this n values has a relation of in multiplication, as in this if it is 2 comma 2, this will be a 4 value. If it is okay, this n value is 8, then this will be 8 comma 8 as in 64 cross 1 vector that you can convert to. So let's have a look at the code. So this is a dictionary for I in the n values. If is strain resize image for digit in the ring strain, okay, resize image reshape to okay fine from 28 comma 28, that is the ideal pixel value of or the given pixel value of the image data set, that then we are converting it into n cross n comma n. So this n comma n values are defined here, then we are flattening that. So basically, we're converting into a number like a vector, and then we are normalizing that. And this is nothing but appending that. So this extend is nothing but appending all the normal vector to a resize vector, and this data set is limited to just the first 100 values, right? And the process data at the end position. So this will be dictionary that we have created, and for each dictionary, this value pair. Uh, so sorry, this key. Whatever indexing we are doing of the key, it will be reproducing the exact circuit for it. So as in if you have put in n is equal to 2, you will be getting a 2 raised to n cross 2 raised to n. So yeah, it is 4 cross 4 circuit what you will be getting, as in 4 cross 4 unitary you will be getting. For n is equal to 4, what you will be getting is a 16 cross 16. No, so that doesn't scale like this. It will be, you will be getting a 16 cross 1. So this scaling I'll have to look into. This doesn't scale as 2 raised to n into 2 raised to n format. It doesn't scale as so what basically I'm trying to tell you is, if it is an image, it is having a 2 cross 2 matrix. So that 2 is written here. If it is having a 4 cross 4 number, that 4 is written here. If it is having an 8 cross 8 number, that 8 is written here. So it will not be a number of qubits. After flattening, after like flattening this, so if it is 2 cross 2, after flattening, what number we get is 4 qubit, 4. So that 4 can be installed in 2 qubits, right? After flattening this 4 cross 4, you will be getting 16. That can be inserted in 4 qubits. But after flattening this, you'll be getting a 64 cross 1 vector that will be installed in just 6 qubits. So that is the only difference you have to take into consideration. Yeah. So now it is clear. So that is the only point. So it is not the number of qubits. It's the first matrix, as in the first you can say number of columns, right? These are nothing but the number of rows of that matrix. Since it is square matrix, so we'll be having the same. So this n values are nothing but that, so no need to confuse. So yeah, hope this is clear. So what n will be having a general notation is 2 raised to n. This n values is nothing but the first the size of the matrix, as in n cross n. So yeah, hope this is clear. Size of the image matrix. I'm talking about the input image matrix. I'm not talking about after conversion. What will be input image matrix? You're flattening that, and the number of qubits should be in that order, as in after indexing it or raising it to the power of 2, it should be a number that is multiple or raising to the power of 2. So all these are can be raised to the power of 2, as in the 4 can be raised to the power of 2, as in this 16 can be raised to the power of 4, and this 8 can be 64 can be raised to the power of 6. Yeah. So hope this is clear. Fine. So this is the fine. We are calling the function. So as we have already mentioned this if statement here. So this if statement is true. So hence it will process all the train data here, and it will process all the test data for n is equal to 2, n is equal to 4, n is equal to 8. Per se, it will be having the input your vectors, input vectors. What we have discussed in your theory is this will be input vectors for the n is equal to 4 qubits, n is equal to 2 qubits, 3 qubits, and 4 qubits. Hope this is clear. And using this indexing 2 comma 4 comma 8, you can access that. Okay, fine. Hope this is clear. Fine. So moving on. So this code per se is for getting that target state. So we have just now what we have done is just getting that input vectors for different qubit sizes for n is equal to 2, n is equal to 3, n is equal to 4. So only first step is done. Now we'll do the same for target vectors, and we'll find the unitaries of separation as well in both cases. So what we'll do first is create the target states. So conventionally, like since the number of classes are less than 16, we can do this of equal spacing, the idea of equal spacing here. But since the number of classes here, or the number of classes of infinite data sets are 10, and 4, like if you write the vector 4 cross 1, it cannot exactly represent if you'll do at equal spacing. So 1 0 0 0 1 0 0 like that, 0 0 1 0 like that, if you represent, you cannot represent this in this format. So what we have done is specifically you can represent other notation, right? So we have like 2 raised to 4, that is 16 states in that, right? So yeah, means as in not 2 raised to 4. So yeah, 2 raised to 4 as in so if you write a vector here. Yeah. Okay. Yeah, if you write a vector here, so that vector is nothing but our 4 cross 1 vector. So you can write basically 2 raised to 4 states in this, right? You can in 0 1 basis. So you can control the zeros and ones, and you can write 2 raised to 4. So as in let's consider this is your first state. Then let's consider 1 0 0 1 is your second state, like that. You can write any like states within 2 raised to 4, like 16 states. You have to represent 10 classes using this as the target state. So since we don't have the compute power, we have included this as well, as in n is equal to 2 qubits as well. So if you would have having compute power, we would have started with yeah, n is equal to 3 is also not possible. N is equal to 4. So anyways, so we have included this, right? And yeah, so these are nothing but your target states. Yeah. So what this specifically function does is create that target state. So yeah. uh, so for I in the range 10, this is your start. So again, for saving your compute power, we are training like what transformers you will be training. It will be limited to just 10 or like 1,000 values. So since your 1,000 vectors of just input, so yeah, and we are not including test data here, right? Because whatever evaluation you can do, you can try putting the same is equal to 3 state, and try finding whether the transformers architecture what you are trained is per se like correct, as in based on whatever output n is equal to 4 state will be getting, 4 circuit will be getting, fine. And this state has been normalized, so you don't need to normalize these states, but you need to normalize this, because this index position is all the remaining are zeros, and only at this position there is one, so you don't need to normalize it. But for this statement per se, this statement is added. Okay, fine. And this is your function call for n is equal to 4, 16 and 64. Oh, so hope this is clear. So next step is constructing the unitary of mapping from the qubit ground state to your quantum amplitude state vector. So what is your qubit ground state? Is nothing but one at the top, the in zero on basis, and remaining all positions will be having zero value in your vector. So this yeah. So basically the code you have to write it if like efficiently, because cascade transfer function we are not utilizing the transfer function here, so this is just a unitary generation code mapping. But for transferring I'll come into detail. So I have transferred, yeah, translation code is there in next node. So this is just a unitary generation code. So what basically this does is, so this is your main operation. So you are already aware about this. So what this does is basically uh, so you know the process for it, right? What is the process for it? So for this, if it's your input qubit count sheet, what you'll be doing is basically writing those all vectors. uh, your data set is limited to 1,000, so you will be having your 1,000 vectors. All the start position will be 1, and remaining all will be zeros, and it will be for this n is equal to 2, n is equal to 4, n is equal to 8. And these are not the number of qubits, these are not the n values what will be matrix dimension. These are the image, like image sizes. So if you're unitary encoding this by following the conventional notation, this will double of that, but it will complicate this further. So let's avoid that. So here we are using unitary SVD for finding the unitary. We are not unitary encoding. The number of qubits remains the same as this. Yeah. So yeah. So where was I? At the start, you will be having 1,000 vectors of this. So yeah, you will be having 1,000 vectors like this. Whose vectors are this setting? So this is just 4 cross 1. right? So this is nothing but your n is equal to means as in 2 cross 2 matrix. For 2 cross 2 matrix, as in the n value is 2, 2. Okay. Now you will be having this similar just 1 and remaining all zeros for your 16 cross 1, right? And those will be your 4 cross 4 pixels, yeah, and the corresponding qubits are nothing but 4 for that, and similarly for 64. So this is your nothing but your input vector, and we already know the like SVD procedure for that. So what exactly is the SVD procedure? If you follow conventional notation, is nothing but output and like outer product of output and input vectors. So then, since this is an array and since these are real, like you can in actual format, what is written there is nothing but transpose of this and multiplied by transpose of this input vector array. So this will be a shape of 1000 comma 4 for start, and then 1000 comma 16 and 1000 comma 64. Okay, this will be your output vectors, and similarly for input vectors. So what exactly are the output vectors? Those you already know. Those are your image vectors, what you are converted. What are input vectors? Those we already know, that those are nothing but this here. So we'll be having 1000 unitaries for n is equal to 3, n is equal to 2, then 1000 unitaries for n is equal to 4, and 1000 unitaries for n is equal to 6. So why equal spacing is taken here? Because you are using amplitude encoding. So for unitary encoding, you have to this first.
Yes, yes.
Yeah. Yeah. So for amplitude encoding, like we are converting or flattening that, right? So that flattening. So you can try incorporating 3 as well. How can you incorporate 3? You can but like, what can be done is you will have to like 8 cross 1 vector you will have to form. So you will have to put that image into root 2 or into so sorry, cube root of not cube root of 2. So this
Yes.
number you have to include. You can write it here 2, 2 is
The
two comma
voice
4.
is echoing.
What? Yes.
Yeah,
Acha,
because my so
okay. Suchi,
so
please turn off your mic.
so 8 cross 1, you can try for n is equal to 3 qubits as well, in which the vector should be 8. Then the image what will be forming is nothing but 4 cross 2 or 2 cross 4. So then that can be done. So I not like we have not done that in the code, but you can try putting that as well. So you can have increase in your data set, as in, and you can try ignoring the n is equal to 6 case, because n equal to 6 case is computationally like expensive. Whatever after translation, even if the cascade code optimization level is 3, that optimization length sequence will be very large. So to avoid that, you can take n is equal to 3 case, and you can take n is equal to 5 case as well. In n equal to 5 case, like so yeah, 32 32 again you have to divide in terms of what you're resizing. So what specifically I'm mentioning here is this n value na, this n value this n value, instead of taking square value, you can try taking a value such that it becomes a multiple of 2 raised to n. That n is nothing but a number of cubes. So hope this is clear. Yeah. So in that case, instead of taking this target states, you can start with n is equal to 2, 3, 4, and 5, and instead of going to 6. So that will be computationally less expensive from this. Okay, fine. Yeah. So this code has been done. Now, yeah. So where were we? Here. So yeah. These are your dimensions, what we already discussed, and this is nothing but forming a. So this for every dimension, it's creating a list in a dictionary. So this is clear. And this device, if you have like a GPU, you can try incorporating this. You can add a like a function there, like if code is available, you can yeah. So yeah. Moving on. So for dimensions for this range, like 2 comma 4 comma 8, if dimension is not in the data, then continue. So this data values what we have taken, so this data values are nothing but your this train data. what we are having in terms of, so previously we have taken this train data, right? 2 comma so this train data is nothing but this here, this. So this will be having an indexing of 2 comma 4 comma 8. So this indexing is followed here, fine. Okay. uh, yeah. So if dimension not in the data continue, then we are entering into the second loop. So this, so we are not having a dimension that is not in the data. We have mentioned specifically 2 comma 4 comma 8, so it will not enter into this loop only. It will execute this. Fine. So yeah, vectors, like what vectors are specifically here, whatever indexing we have done. So uh, this is a dictionary. This data is nothing but dictionary, and this is the key value of whatever. So train data we are like inputting here, and this is nothing but 2 comma 4 comma 8. So this will be your corresponding vectors, will be your 1000 comma that 4. So for start it will be 1000 comma 4 in the first setting, and then the input vectors, like you already know, the input vector remains fixed, only the input vector size changes. So this is nothing but a dynamic variable assigned here. So whatever size will be assigning here for data, so the data dimension, automatically the size will be taken here. So hope this is clear, and this will be your input state, that input qubit ground state. And then we are entering the loop, because like what we want per se. So why this is specifically done is nothing but batch sizing. So to save the computational power, instead of taking the for taking the chunk size, we can do it in one go itself, but it will be computational accuracy. So we have taken this. So like for input vector chunk, so this is your like output vectors, this is your input vectors, you already know. And this is your non-entry. So what this torch ensum basically done like does, you can check out the ancient notation for it. So what this basically does is we already explained, like this will give us the output vectors, like auto producted with the input vectors. This is your non-unitary, and to get a unitary from it, you can apply svd of that non-unitary. And then at that particular dimension, so similarly we have made a dictionary of that. So at that position we'll be appending your producting your unitary and vh. So hope this is clear. And to increase the precision, this float 64 is utilized. So by increasing the precision, it will be helpful for you in reducing the token size, because the circuit will be accurate, as in the difference error rate will be reduced. Because if the error is introduced here itself, then the error will propagate further, and then the period value should be kept like lesser. So token size will increase, so it will again increase the computational. So since this is a research phase at the start, we can try an error, like trial and error, and we can see. So yeah. So these are all for concatenated in unitary dimension. So hope this is clear, and this is similar done for your target vectors. So code will change little bit, because your target vectors are already defined, as in this target vectors are already defined here. This, so these target states are already defined, and this is nothing but past, later, and as well. So yeah. So hope this is clear. Similar steps are done in this as well. So what basically these two will be giving you your unitaries. So one more point in using float 64, if you use float 32, then whatever unit you will be getting, if you multiply u into u dagger, you will assert that check. Then you will be like having that I value, whose Frobenius norm will be 1 e to the 6, 1 e to the 7. So that unitary will not be considered as a unitary in cascade transpiler. So you will get an error here, like that unitary is not a transpiler, not a unitary. So it will consider that as a non-unitary matrix. So for getting or avoiding that error, a higher precision value is used. So yeah, so that factor also needs to be like incorporated for higher number of qubits as well. So where we require more precision, because after a certain range, the unitary values, as in for 10 qubits, 20 qubits, or 30 qubits, the unitary values what we'll be having are very less, like 1 e to the 16, 1 e to the 17, in that range. And if you will be having error range of 10 to the minus 6, then like whatever unitary will be getting, it will be similar to not applying unitary itself, which will be some random unitary application. So that level of precision also need to be incorporated in the code. So yeah, it needs to be incorporated at the time of scaling. So that is one more research point of view. Yeah, fine. So moving on, so we are directly like using the Criskit transfer layer, and they have already introduced that optimization levels here. So what basically the optimization level does is control depths of the circuit. So yeah, so this transfer circuit, we have directly called the function, so you can have a look at the code written here. So specifically for n is equal to 6 qubits. So yeah, so this is the main point of conversion. So then what we discussed earlier, na, the point is implemented here. So if n is equal to 6 qubits, because we already know that 2 comma 6 comma 2 comma 4 comma 6 are nothing but not qubits. They are not qubits. They are the n values of the image matrices. So n is equal to 6 qubits is not there. So we are adding 2 in that to like make it 8 qubit circuit. As in, okay, just give me a sec. Yeah, so sorry, the indexing position of the unitary dictionary. So this indexing position, this is already know, this is a dictionary. So this keep like value we already know, it varies from 2 comma 4 comma 8, but number of qubits we already know that is 2 comma 4 comma 6. So that no, that 2 is added for the indexing here. So hope this part is clear. So if n equal to 6 qubit, then it will enter the loop, otherwise it will not. And the remaining translation operation is done here. You can go through the code. And this so I had tried one this like Possum string writing in algebraic notation format. That's a different from what we were expecting to write, but it again shows the like computation error, because translation function you can try incorporating some kind of delay here. So this delay is also incorporated, or you can find other ways to optimize the code. But in my laptop per se, like the code was giving error, memory error. So yeah, execution error as well. So like I stopped at that point. So it's up to like you guys to research this further, like how to convert this transfer circuit. That transfer circuit you can print it in terms of, you can save in terms of notebook, but that notebook conversion, or that particularly that U3 that angle conversion to tensor notation format. So that tensor notation format, how many ways are there, like you can explore that, and that similar like research statement is given here. So you can try researching that, and these are your again task explained here. So whatever explained in the notepad, the 4 or 5 pages whatever are explained, apart from that, these are your tasks. Like in the transformer architectures as well, like there are many points to focus on, but apart from that, like this is your like task. So yeah, so hope this is clear. 1.5 months is limited time for all this, but the in-depth research you will do, it will be like you will be getting more intuition, more new things, like you can try implementing in this problem sheet. So hope this is clear, Suji.
Yes, actually, thank you so much. It
Okay,
was amazing session.
thank you.
Yes.
Thank you. Thank you, Akshay.
Yeah,
So
thank you, man.
I think I will
I
stop the
think I will
recording now.
stop the recording now.